Hello everyone from Math 2000. It's linear algebra. Professor Wenson here again with a video on your ZyBooks Section 2.5 titled Solving a System Using an Inverse Matrix. Alright, so we've seen inverses and how to find the inverse of a square matrix. And some square matrices have inverses and some do not. We'll look here at systems of equations where your coefficient matrix is a square matrix, and if it's invertible, right, if it has an inverse, how can we use that to solve the system? All right, so if you recall from a section or two ago, you can write a system of linear equations as a matrix equation, right, where you have a matrix A times variable column matrix X equal to a column matrix of constants B, right? And matrix A was the matrix of coefficients, right? The coefficient matrix. If A is square, right? If A is square, so 2 by 2, 3 by 3, so on, then it might have an inverse. It might have an inverse. If A inverse exists, the column vector of variables x can be solved for using that inverse, right, along with the column vector b. So here we're going over two objectives in this section. One, represent a system of linear equations using a matrix equation, which you've already done. I don't know why this is coming back, but and then two, use an inverse matrix to solve a system of linear equations. All right, so if a system of linear equations has the same number of variables as equations, so the same number of variables as equations, then the coefficient matrix in the corresponding matrix equation will be square. In this case, a method for solving the system using inverse matrices can be derived as follows. Right? So big if A inverse exists, then you can solve for x. You can solve for the variables by multiplying both sides on the left by A inverse. And multiplying by A inverse makes the identity matrix on the left, so that just leaves you with the variables. And then on the right you'll have A inverse times B. A inverse on the left, B on the right. But that's only if A inverse exists. Right? So if you have a square coefficient matrix and that matrix is invertible, your system will have one solution, and namely it'll be A inverse times B, the inverse matrix times the constant column on the other side. If the square matrix is not invertible, then the system of equations will have either no solution or infinitely many. Okay. So remember, we've talked about this before. This has come up before. For any system of linear equations, you either have no solution, exactly one solution, or infinitely many. All right. So in these systems with a square matrix as the coefficient matrix, the only time you're going to have exactly one solution is if that matrix has an inverse. All right. And if the matrix does not have an inverse, well, then you could be in a situation where you have no solution, or in the situation where you have infinitely many. You'd have to figure that out by making an augmented matrix and then putting it in a reducer echelon form, or echelon form, and solving by back substitution. Right? We've seen how to solve systems before. All right, but this is just adding on. Well, what if we have a square system with an invertible coefficient matrix? All right, so for example, right now I know that here they give us the inverse. I'm going to actually do this on my own on a separate sheet of paper and show you how I would go about solving this system with an inverse. So let me write it here. Okay, so this is a matrix, not a matrix. It's a system of equations that will have a square coefficient matrix, right? The number of variables is equal to the number of equations, right? There are two variables, two equations. So as a matrix equation, hopefully this sounds familiar, right? It looks familiar, right? I write my coefficient matrix. So down the first column, the coefficients of x1, right? 3 and 1. Down the second column, the coefficients of x2, -1 and 2. Multiplied by the variable matrix, x1, x2. And this is equal to the matrix of constants, 5, 4 here. So this is in that form, matrix A, right, the coefficient matrix called A, times the variable vector, called x, equals, and then the constant vector, called B. So notice again, A is square, right? A is a 2 by 2. So the big question becomes, is A invertible? So hopefully you remember how to do this from last section, right? Remember, you take the product of the diagonal entries for a 2 by 2 and then subtract the product of the non-diagonal entries. So I take 3 times 2 minus, -1 times 1. That's 6 plus 1, that's 7. And that product, right, that expression, the 3 times 2 minus -1 times 1, the A times D minus B times C, if you remember that from last section, that's not 0. That means that A is invertible. A inverse exists. And if A inverse exists, that means that this system is going to have exactly one solution. This means the system will have exactly one solution. There's only one solution. Right, and we're going to find it using the inverse this time. Right? I know you know how to solve this another way. Right? We could make the augmented matrix, put it into echelon form and solve by back substitution, or put it into reduced row echelon form. You can do that if you want all the time. We're just going over a different method here. Now A inverse. And I'm not going to remember the formula from last time. I take this number, this A times D minus B times C, the 3 times 2 minus -1 times 1, 7. I take the reciprocal of that, right, 1/7, times another 2 by 2, where I switch the main diagonal entries, so it becomes 2 then 3 here. And then the other two entries are just opposites, +1 in the upper right and -1 in the lower left. This is A inverse. I'm going to multiply both sides on the left by A inverse. So I'm going to multiply on, again, order matters, so the position matters. So you see I'm multiplying the left of both sides here by A inverse, and it's got to be on the left. Right? And that'll turn, right? That'll turn this matrix. Right? I'll have A inverse times A. That's just the identity matrix, right? When you multiply two inverses, you get the identity matrix. So all I'd be left with is the variables on the left side and the solution on the right. And that's what they were saying earlier, right? So this system has only one solution. The variables will be equal to whatever A inverse times B is. Right? And let's figure that out on the next page. So if I do that, I multiply both sides by A inverse on the left. We're going to get, the variable matrix alone on the left side equals, and then, A inverse times B, 1/7 multiplied by the 2, 1, -1, 3 times B, right? The constants, the constant matrix there is 5, 4. And that's 1/7 times, if I multiply these two matrices here. Now it's a 2 by 2 times a 2 by 1. So that'll be a 2 by 1. And it should be a 2 by 1 because this is a 2 by 1 on the left side, right? If they're equal, they should both be the same size. And first row, first column would be 10 plus 4, right? 14. And second row, first column would be -5 plus 12, which would be 7. and multiplying this each entry by 1/7, we're getting the solutions of 2 and 1. All right, so x1 would be 2 and x2 would be 1. And there's the only solution to this system. And we can double check. All right, go plug them in. Plug in 2 for x1, 1 for x2. That'd be 6 minus 1 is 5. Fantastic. And then 2 plus 2 is 4. Also great. This is a good, valid solution. And it's going to, again, it's the only one. If you have a system with a square coefficient matrix and that matrix is invertible, if A inverse exists, there's only going to be the one solution, A inverse times B. A inverse times that constant matrix. Okay? Alright, so that's what they're doing here. When you read through this example, see the 2, 1 at the end there. Alright, then we're asked to do the same thing here. Alright. Now again, you should be able to find the inverse if it exists. Alright, now be careful with this. They have part of the solution already, so I'll just do this one more and show you what you're filling in here. Alright, so let's go back and do this system. Alright, so here's this system, and again, as a matrix equation, 3, 1, 1, negative 4. There's your coefficient matrix, and again, notice it is a square times the variable matrix x1, x2 equals, and then the constant matrix 2, 5. So here's your A times variable vector x equals constant vector b. And the big question is, A is square. Is A invertible? All right. If you have a square coefficient matrix, this should be the first question you ask yourself. Is A invertible? So I take that A times D minus B times C thing, right? 3 times negative 4 minus 1 times 1. This is negative 12 minus 1. That's negative 13. That is not 0. And if that expression is not 0, then A is invertible. A inverse exists. Okay. Meaning, again, this system will have exactly one solution, where I multiply on the left by A inverse. Right? I multiply both sides on the left by A inverse, and that'll turn this into the identity matrix here, leaving me with the variable by itself. The variables by itself equals A inverse times B, whatever that is. All right. So then what would be A inverse? Right? Again, formula from section 2.4. Take this negative 13. The reciprocal of that would be negative 1/13. And this was again, this is only for 2 by 2s, this formula. Right? And then I switch the diagonal entries, right? Negative 4 here, positive 3 there, and then the opposites of these two, negative 1, negative 1. There's A inverse. Okay. Now they give you a version where they put the negative inside. If you look at, see how it's positive 1/13, but then this is positive 4, positive 1, positive 1, negative 3. So like all the opposites of what I have here. So all they did was put the negative inside and give me this version, right? Positive 1/13 times positive 4, positive 1, positive 1, negative 3. So same thing. Right? All right, so I'm going to use this. I'm going to multiply on the left side. That'll turn this left side here, this into the identity matrix. So I'll be left with just the variables. Right? Just the variable matrix. So on the left side I'll have x1, x2 equals, and on the right side I'm doing A inverse times B here. So the A inverse is this 1/13 times the matrix 4, 1, 1, negative 3 times B is this constant matrix, the 2, 5. Alright, so this is 1/13. And I multiply these two. A 2 by 2 times a 2 by 1 will be a 2 by 1. First row, first column will be 8 plus 5 is 13. Then second row, first column is 2 minus 15 is negative 13. So my solution is x1 equals 1 and again multiplying both of these by 1/13, and x2 equals -1. So x1 equals 1, x2 equals -1, and that's the only solution to this system. And double check it. Plug in 1 for x1, -1 for x2. That'll be 3 minus 1 plus -1 is 2. That's good. And then 1 plus 4 is 5. That's good too. Right, that works out. But that's how the inverse is used. Right. Again, only if the square matrix actually has an inverse. If it doesn't have an inverse, right? If this expression, the A times D minus B times C, if that's equal to 0, then A inverse won't exist, and you'll have to do it the old-fashioned way, right? You'll have to do it the way we've been doing it in previous sections, where you make an augmented matrix, put it into some echelon form, and go from there. Right? Okay. Then back here, now the way they're having you enter here. See, they gave me x1 is 1. All I have to enter is the second blank, which would be for x2 was -1. Right? That's the only thing I have to enter. They don't have you entering the whole thing. So here, see, they give me, there's x1 and x2. They give you x2. You just have to plug in x1 using this inverse. All right, and this is no different. All right, this is no different. Now remember, you should be able to find inverses yourself. All right, you should be able to find inverses yourself for a 3x3 or 4x4. Remember that augmented matrix method where you put the matrix down on the left, you have the identity on the right, and then you put it into reduced row echelon form, and hopefully then you'll have the identity on the left and the inverse on the right. Again, look back at section 2.4. But here we're given an inverse again, so this time I'll just actually work through where we're given an inverse. All right. So again, this kind of problem, you have the value of x1 given to you, the value of x3 given to you. I'm just asked for the value of x2. But I'm going to write this out and go through it the way I would if I wasn't given the inverse. All right. All right, so again, I've written out that system, and I did it so that all the like terms lined up. I made it look a little better than they did. As a matrix equation, right, you have the coefficients of x1, 5, 1, and 0. Coefficients of x2 down the second column, 6, 2, and 1. Coefficients of x3 down the third column, 0, 3, and 4. Times your variable matrix, x1, x2, x3. Equals, and then the constants, -3, 0, 1. Alright, so here's the coefficient matrix A, right, and it is a 3x3. It is a square. Times your variable matrix, your variable vector x, equals the constant matrix B. Again, I'm going to ask myself, can you find A inverse? Right? Find A inverse if it exists. If it exists. Now remember how to do that. All right. So I'll refresh your memory. Write out the method, right? For larger matrices, matrices larger than a 2x2. So far, the only method we've seen, and we'll see more methods for finding inverses later, but was the that augmented matrix method where I put matrix A on the left, the 5, 6, 0, put a little bar here. 1, 2, 3, 0, 1, 4. And then the identity matrix on the right, the 3x3 in this case, because it's a 3x3. So 1, 0, 0, 0, 1, 0, 0, 0, 1. So the matrix A on the left, the identity matrix on the right. And then you perform row operations. Now I'd have the calculator do it, for here just to save some time, but you should be able to do this by hand as well. I perform row operations to get this into reduced row echelon form, and based on what I'm looking at, I'll write out what you're going to end up with. You should end up with, if it's invertible, right? If the inverse exists, you'll end up with the identity matrix on the left, right? If the inverse exists, you'll get the identity matrix on the left. If you don't get the identity matrix on the left, then the inverse doesn't exist, and then the system would either have no solution or infinitely many solutions, right? Instead of just the one solution. And on the right should be whatever the inverse is, if it exists. In this case, it would be 5, negative 24, 18, negative 4, 20, negative 15, and then 1, negative 5, 4. Right? So here, this 3 by 3 is A inverse. So I'm going to go back to the original system, right, and multiply on the left. Since A inverse exists, I can use it. Multiply both sides on the left by A inverse. All right, so in doing that, we get the following. We get this the x1, x2, x3, the variable matrix is equal to, A inverse times B, right? A inverse times B here. So A inverse is this 5, negative 24, 18, negative 4, 20, negative 15, 1, negative 5, 4. There's A inverse times B, the constants, right? This matrix with the negative 3, 0, 1 on the other side, that was the B. Right? And this is a 3 by 3 times a 3 by 1, so it should be a 3 by 1. Alright, so first row, first column, you'd have negative 15 plus 0 plus 18, that'd be 3. So that'll be the value of x1 in the solution to this system. Second row, first column would be 12 plus 0 minus 15, that'd be negative 3. So the value of x2 in the only solution to this system would be negative 3. And then the third row, first column would be negative 3 plus 0 plus 4, that's 1. All right, now the only thing missing was the negative 3 back on the assignment. All right, so you see that 3 for x1, 1 for x3, and we saw negative 3 for x2. All right. Okay, and then you have to do the rest. Right, there's only one more left. All right. Then you have your challenge activity. Now, if I hit start here, now it looks like this first one is pretty simple. Doesn't look like I have to solve anything. It's just complete the coefficient matrix A and the column vector B for the following system of equations. All right. So down the first column, the coefficients of x1, so 1 and 3. 3. Down the second column, the coefficients of x2, negative 2 and negative 5. And then over here, what would be the constants? You'd have your variable matrix, x1, x2, and then over here the B would be the constants, 2 and negative 3. And that's that simple for that one. Okay, wow. I hope they're not all that easy. So let's see the next one. Yeah, see, now you're asked to find A inverse. So remember, A is the coefficient matrix with the negative 9, 7 down the first column, negative 4, 3 down the second column. All right, and then yeah, you can find A inverse. All right, and then they might ask you for solutions in the last two. So again, I'll leave that to you. All right, and the last part is on balancing chemical equations using inverse matrices. So I'm actually going to go over this first example, and I'll leave you to the participation activity because then it's over. All right. So let me go over this first example. So remember, balancing a chemical equation, all right, requires finding the correct coefficient for each molecule so that the numbers of each type of atom on either side of the equation are equal. All right. So we don't know what these coefficients are. So I'm going to write this out, all right, this chemical equation here, and we'll see what numbers do I need to put on these molecules so that the number of atoms of carbon on the left is the same as the number of atoms of carbon on the right, and the number of atoms of hydrogen on the left is the same as the number of atoms of hydrogen on the right, and the number of atoms of oxygen on the left is the same as the number of atoms of oxygen on the right. So I'm going to have several equations to write here. All right, so here's the chemical equation that's given in this example. Now look at right now. See how there's the C8, this molecule with 8 atoms of carbon and 18 atoms of hydrogen. I honestly don't know what this is called. Plus oxygen, right? O2, two atoms of oxygen. How many of those do I need? Will yield carbon dioxide and water. Right? We'll react together to produce just carbon dioxide and water. But how much? All right, we need to figure out what are the coefficients, because right now it's not balanced. Right now it is not balanced. See how there are 8 carbon atoms on the left side, but there's only 1 carbon atom on the right? There are 18 hydrogen atoms on the left. There's only 2 on the right. There are 2 oxygen atoms on the left, and there are 2 here, 1 there. There are 3 on the right. This is not balanced. So I'm going to put, and they said, let's use variables, because I don't know what the coefficients need to be. I don't know how many of each molecule I need. So there, I'll say, let's call this X. X is the coefficient of this molecule here, the C8H18, plus Y times the O2. How many O2 molecules are there? And what it'll yield is Z molecules of carbon dioxide plus W molecules of water. So again, X, Y, Z, and W are going to be numbers, coefficients, the numbers of molecules. And this is another key. They're numbers of molecules. You can't have half a molecule of something. You can't have 3/5 of a molecule of something. The coefficients have to be whole numbers because we're talking about numbers of molecules. Right? Whole numbers of molecules, but the key being whole. All right, so when I solve this, when I figure out what X, Y, and Z, and W could possibly be, I have to set it up. I have to figure it out a way so that the solution has all whole numbers, no fractions. All right, because you cannot have a fraction of a molecule. All right, so I'm going to write some equations here. Now again, instead of X, Y, Z, and W, you could have called these X1, X2, X3, and X4. It doesn't matter. So one will be equation for let's say for each type of atom. So I'll start with the carbon atoms. On the left side, there are 8 carbon atoms in every molecule of this, and there are X of these molecules. So there are 8 times X carbon atoms on the left side, and I would like this to be equal to the number of carbon atoms on the right side. And carbon only shows up in carbon dioxide here. Now, there's 1 carbon atom in every molecule, and there are Z molecules, so 1 times Z, or just Z. So this is the number of carbon atoms on the left, 8 times X, should be equal to the number of carbon atoms on the right, which is Z. All right, then we have hydrogen. So there are 18 times X plus, there's no hydrogen in that molecule, so there's 18 times X hydrogen atoms on the left side. And on the right side, the only place hydrogen shows up is in this molecule, and there's 2 of them there times W molecules. So this is equal to 2 times W. There are 18 times X hydrogen atoms on the left, 2 times W hydrogen atoms on the right. And those should be equal if this equation is going to be balanced. And finally, the only other atom that shows up here is oxygen. There are 2 times Y and nothing else. There's no other molecules with oxygen on the left. 2 times Y atoms of oxygen on the left. And oxygen shows up in both of these. So there's 2 times Z oxygen atoms from these carbon dioxide molecules, plus, and then just W. Right? There's only 1 oxygen atom in each molecule of water times the W molecules. Right? So there's 2Z plus W oxygen atoms on the right, and I want them to be equal. All right. So what we have here is there are 3 equations, there are 4 variables. So the number of equations isn't the same as the number of variables. So you'd think, hey, I thought we were doing square systems. We are. So I mean, you could solve this. You could solve for x, y, z, and w here the old-fashioned way. All right, you can just take everything on one side, 0 on the other, and use augmented matrices and put things into reduced row echelon form. But what I'm going to do, just so we can use inverses, I'm going to do this the way they're showing here. I'm going to take just 3 of the variables to one side, because there are 3 equations. I'm going to take just 3 of the variables to one side. So just manipulating these equations, I'll get this system. Let's just say I take the x, y, and z. Let's just take the x's, y's, and z's to the left. And I'll leave the w's on the right. All right, just so I have 3 equations with 3 variables on the left side, and the 4th variable would be on the right side. So we have 8x, and then no y, and then I'm subtracting z. I'm taking all the x, y's, and z's on the left, and then you have equals 0. Second equation, you have 18x, no y, no z, and then the 2w on the right side. And then third equation, take the x, there's no x, you have 2y, then I'd have minus 2z equals, and then over here, just w. All right. Now, as a matrix equation, over here, where I have the coefficients of x, 8, 18, 0, coefficients of y, 0, 0, 2, and coefficients of z, -1, 0, -2, multiplied by what variables are in here. That's x, y, z column, so the x, y, z matrix, right, equals, and then over here, all these have a, technically that's like 0w. All these have w in common. So I could pull a w out as a scalar and have it be multiplied by the vectors 0, 2, 1. All right, you see how that's 0, 2w, and 1w. Okay, so again, you could have taken everything to one side, all the variables, and done it the old way. All right, you could have. That's not wrong to do. All right, but I'm only doing this so that way we have one of these sides with a square coefficient matrix. Right, that is a square matrix, and again, I'll call this A. And I know there's a W here, so keep that in mind. But I'm going to call this B, right, and we'll call this X. So let's find A inverse. All right, so I'm just going to have that on the calculator. I'm going to say find A inverse. If it exists, right? If it exists. Because if it doesn't, then I'd have to solve this some other way. I can't use an inverse if this square matrix doesn't have an inverse. If it exists. All right, so I can use a calculator. All right. Now, when I use the calculator, I come back with this, and I'm just going to have the calculator spit it out to me. And you should be able to do it by hand, right? You should be able to do it by hand, but just to save some time, I'm going to do it on the calculator. All right, so I entered this into my calculator, saved me some time here. I got A inverse. The inverse of this square matrix on the left here is the following: 0, 1/18, 0 for the first row. Then next row, -1, 4/9, then 1/2 for the second row, and -1, 4/9, and 0 for the third row. All right, it does exist. And then I'm going to multiply both sides on the left by this A inverse. Okay, now W is just a number. Remember, W is just some coefficient, just some number. So I can pull the W out front, and we get the following. Right, when you multiply these two, right, the A and A inverse, that's going to be the identity matrix. So that's going to be, those are going to be gone. And on the left side, I'll have X, Y, Z on its own equals, and like I said, W is just a number. W represents a number. So I can pull the W out front, times, A inverse times the 0, 2, 1. Let's see what we get. So this is equal to W, and when I multiply these two, now again I'm going to kind of do it out in my head here. This is a 3 by 3 times a 3 by 1. This will end up being a 3 by 1. First row, first column, I'd have 0 plus 1/9, 2/18 plus 0. So that's 1/9. All right. Then first row, second column, you'd have a 0, then 8/9 plus a half. All right, 8/9 plus a half. Getting a common denominator, that'd be 16/18 plus 9/18. That'd be 25/18. All right, 25/18. All right, and then the third row, first column, you'd have 0, then 8/9, and 0 again. So just 8/9 at the end. All right, so here we have our solutions, but in terms of W. So remember, W is kind of like a free variable here, right? So I can pick W to be any number I want. But remember what I said at the very beginning of this example. These are coefficients, these are numbers of molecules. You cannot have fractions of molecules. So I'm going to choose a value of W. Choose W so that all the coefficients are whole numbers, right? Because these are again counting numbers of molecules. So in that case, I want to get rid of these fractions, and that would mean let W be the least common denominator. Let W be 18, right? Or any multiple of 18 really, but the smallest one is 18. So if W were 18, then you'd have X, Y, Z would be equal to 18 times this. Now 18 times a ninth is 2. Times this, the 18s would cancel, you'd have 25. And then times this, 9 goes in 18 twice, 2 times 8 is 16. So X equals 2, Y equals 25, Z equals 16, and W equals 18 would balance this chemical equation. And let me put that in and we'll see. Let's put that in and we'll see that the equation is balanced with these coefficients. Like I said before, you didn't have to solve it this way, but I only did it this way so we could actually use an inverse. You could solve this in the way we normally solve a system from earlier sections. So let's check it. All right, so if X is 2, all right, so I have what I have 2 in front of the first. So we have 2 C8H18 plus, and then how many molecules of O2? That was Y, so 25 molecules of O2 should yield or produce. And then we have Z times the CO2, the Z is 16 here, 16 CO2s, plus, and then how much water, which was W, 18 molecules of water. Let's see if this actually works. So how about the carbons on both sides? Well, there'd be 16 on left, 16 atoms of carbon on the left side, right? 8 times 2. And 1 times 16, right? There's 16 on the right side. That's good so far. How about the hydrogen? There are 36, right? 18 times 2, there are 36 atoms of hydrogen on the left. And there are 2 times 18, 36 atoms of hydrogen on the right. Fantastic. So far, so good. And how about the oxygen? There are 50 atoms of oxygen, 2 times 25 on the left. On the right, there's 32, 2 times 16, 32 plus 18. All right, 1 times 18. 32 plus 18 is 50. There are 50 atoms of oxygen on both sides. So all the atoms are balanced This is a balanced chemical equation. Right. And again, I could have picked W to be any multiple of 18. All right, that would have made all these whole numbers, but the smallest one was nicest. Okay. All right, so that's just one example, and they have another one coming up, right? In the participation activity that you can do on your own. It's a lot more. Now here they consider, instead of like doing phosphorus and oxygen separately, they say, hey, do oxygen, do hydrogen, do calcium, but this PO4, this I don't even know. Again, I don't know what that's called. Chemistry guy, sorry. But they say, hey, consider the PO4 to be its own thing. All right. And then they have the statements here. See, treat PO4 as a single element, and then work with PO4 as its own thing, calcium, oxygen, and hydrogen to get the four equations that they have here. All right. And at the end, I'll just tell you right now. See these last parts. Yeah, they got the solution here. Maybe, I don't know if that's true or false, but the last part, this can't be happening, right? If you're trying to balance a chemical equation, you're not going to have 4/5 of a molecule. You're not going to have 7/5 or 1/5 of a molecule. All right, so this can't be a good balanced equation. Sure, your solutions might be solution to the system, but they don't make a chemical equation balanced if they're not whole numbers. So automatically I'm putting false for that one. Because again, fractions of a molecule do not exist. All right, and then you have your additional exercises. Some of these are on assignment 4, right, which you'll be submitting to me, uploading to me. A lot of them aren't. I still recommend that you do all the problems, because you can check the solutions to see how you're doing, see if you're grasping it. And of course, if you have any questions, let me know. And please, 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 right? Please, I ask this every time. Please work on the problem. Try to do it before you look at the solution. All right. Don't just copy solutions. You're not going to learn anything if you're just copying solutions. All right, and that's it for section 2.5 on how to use an inverse if it exists, right? If it exists. How to use the inverse of a square matrix to find a solution to a system of equations. So hopefully this video is a good enough guide for you to get through this and help you with working on the assignment problems. And let me know if you have any questions throughout the week. Thank you for watching.